All right, in this video, we'll be going over section 5.2. In section 5.2, we are going to learn another technique that we can use to integrate products of functions, which is called the integration by parts. Okay, we'll be talking about the technique integration by parts in this video. All right, I want to start with this particular theorem. Theorem 5.6, reversing the product rule. Okay, here is what the theorem tells us. If u and v are functions such that u prime of x times v of x plus u of x times v prime of x is integrable, then the integral, indefinite integral of this function, which is this one, is equal to u of x times v of x plus c. Would you believe in this formula? This formula is obviously true because this is an antiderivative of this function. As you can see, if you differentiate this function, you exactly get this function. That means this is an antiderivative of this function. What that means is that the indefinite integral of this function is equal to that antiderivative plus a constant. Okay, that's by the definition of indefinite integral. And this is what we call the kind of undoing the product rule. Okay, reversing the product rule. We have a product here. The integral of the product is equal to the product of those two functions plus c. Okay, here is an example. We all know that the derivative of this product x times sine x is derivative of x is 1 times sine x plus you leave x fixed and take the derivative of the second function, which is cosine x. Now, if you integrate this function over here, you should get your original function. X times sine x, of course, you have to have a plus c because you are talking about an indefinite integral. Okay. So this is what we call the undoing the product rule. If you know that you have a derivative of a product, this is a derivative of the product, derivative of this particular product, then the integral of this piece would be your original function, x times sine x plus c. All right, this theorem motivates us to the integration, idea of integration by parts. Okay, so now let's go over this theorem, which states the integration by how to do the integration by parts. Formula for integration by parts, theorem 5.7, by the way. If u is equal to u of x and v is equal to v of x are differentiable functions, then integral u dv is equal to uv minus integral v du. Okay, this is what we call the integration by parts formula. This is the formula that we'll be applying throughout this section. For all the examples, we will be sticking to this particular formula. All right, how is this formula true? Well, it's a straightforward implication of this formula that we discussed in the previous slide, that is undoing the product rule. Okay, if we have the integral of this function is equal to u of x times v of x, that's true because we know that the derivative of this is exactly this function. Okay, so now what you do is you basically send this term, send this particular term to the other side. You send this term to the other side. If you move this term to the other side, let me write down what I get. All right, I moved this part to the other side. Since we have two integrals in both sides, I don't really have to put this constant because when you do the integration, you are going to put a constant anyway. Okay, now let's observe a few things. From the previous section, we know that v prime of x dx is nothing but dv. Here you have u prime of x dx, which is du. We know that from the previous section. So I can put du here and I can put dv here. And also, of course, my u of x is nothing but just u. Okay, so if you plug that in, this is the formula that you come up with. Okay, this is what we call the integration by parts formula. So in this section, we will be seeing many examples where we can apply this integration by parts formula. We use the integration by parts formula to integrate products of functions. in particular products of functions that we cannot integrate with U substitution. Okay. Here is the first example I want to look at. How do we integrate a function like this? Well, clearly, if you try to use the U substitution, you will realize that U substitution is not going to work here. Okay. So you can use integration by parts formula to integrate functions of this form, x times cosine x. Okay. So what we do is we always compare the given integral to the left-hand side of the integration by parts formula. Here is the left-hand side of the integration by parts formula. You compare this one against this one. And then you try to identify u and dv. That's the whole point here. So here in this case, what I'm going to do is I'm going to take my u to be x and rest of the thing to be dv. I'm identifying my u to be this one, x, and then dv to be this whole thing, cosine x times dx. So here is the identification, u is equal to x, dv is equal to cosine x. Now what I do is I differentiate my du. I can immediately find du over dx, which is x. And from the other one, I can anti-differentiate both sides. If I anti-differentiate the left-hand side, the integral of dv is just v. We know that it's just 1 times dv. That is v, if you integrate that. Okay. So the left-hand side is, of course, v. And the right-hand side, if you anti-differentiate your right-hand side, integration cosine x dx is sine x. So we find v. By anti-differentiating this expression, we find v to be sine x. That's the first step in the integration by parts procedure. Okay, when you apply the integration by parts formula. So you identify your u. I identified my u to be x here. I find immediately du over dx to be 1, of course, here. It should be 1, okay? And then from the other one, I find my v by anti-differentiating both sides or integrating both sides. If you integrate left-hand side, you get v. If you integrate right-hand side, integration cosine x dx is sine x. So we have all the data I need to go with the integration by parts formula. Now let me apply the integration by parts formula. Okay, by integration by parts formula, I identified this to be my u and this to be a dv. Then that should be equal to, this should be equal to uv times integration v du. So let me apply that formula. So that means x times cosine x dx. Notice that this is nothing but integration u dv, because I identified my x to be u and dv to be this whole thing. So this is same thing as integration u dv. That's what I have here. So that should be equal to uv minus integration v du. So this should be equal to uv. What is my u? What is my v? U is x, v is sine x. You see what? Now you need to be able to understand why I found my v, because I need v in this formula. I need to plug in v here. That's why I anti-differentiated this equation to find my v. U times v, which is x times sine x minus integration v du. What is my v? V is sine x. What is my du? Here I have du over dx is equal to 1. That means du is equal to, of course, I should have simplified this one. This means du is equal to dx. I just multiply this to the other side. You get du is equal to dx. Okay, so that means in this formula, du is nothing but dx. So that is dx. So that's the integration by parts formula, the first step of the integration by parts formula. Now, as you can see, this integral is easier to calculate than this one. Here we had a product. We had no clue. But here, when you apply the integration by parts formula, now we have only one integral. This is something that you know. You know how to integrate sine x. We have a formula for that. So we can apply that formula to get the final answer. X sine x minus the integral of sine x is minus cosine x plus c. Of course, you should have a constant. So that means that is equal to x sine x plus cosine x plus c. That's your final answer. And that's how you use the integration by parts for a product. Okay, it's all about identifying your u and dv appropriately. Okay, you need to identify them in the right way. If you make the incorrect choice, then that will not lead to a solution sometimes. All right, let's move on. All right, let's work on these two examples. Use integration by parts to find these integrals. So let's work on the first part. A. Again, here is the integration by parts formula. I have given it here. So all what we need to do is you need to compare your left-hand side with this integral and identify your u and dv. So in this case, I'm going to identify my u to be x. You might be wondering, why don't I identify e to the power 2x to be u? If you do that, you will see that when you apply the integration by parts formula, you will come up with a complicated integration than this one. That's not what you want. You want a simpler integration than this one. That's the reason why for my choice u. I'm going to take u is equal to x. And I would encourage you to try by taking u is equal to e to the power 2x and see what happens. You will see that you are going to come up with an even complicated integral. So immediately I can find du over dx is equal to 1. That means du is equal to dx. And then I identify my dv, this component, to be e to the power 2x times dx. I identify my dv to be e to the power 2x times dx. Okay, what did I do? I identify this to be my u and this whole thing to be my dv. From this one, I can anti-differentiate to find my v. Okay, if I integrate both sides, integration of this side is just v is equal to integration of the side right-hand side would be e to the power 2x divided by 2. That way we find the function v. Remember, that's all we need to apply the integration by parts formula. So let's write the left-hand side, which is exactly this one, that is equal to, now I go with the integration by parts formula, x times e to the power 2x dx is equal to, this is equal to this one by our identification, that is equal to u times v minus integration v du. U times v. I have both u and v. U is equal to x, v is equal to this function. So u times v would be x times e to the power 2x divided by 2 minus integration v du. V is e to the power 2x divided by 2 du. What is my du? My du is exactly dx. As you can see, this is a simpler integral than the original integral. Okay, that's the purpose of integration by parts. Okay, that will bring your original integral down to a simpler integral. Now I can deal with this easily. I know how to integrate functions like this. So this will be equal to x times e to the power 2x divided by 2 minus 1/4 times e to the power 2x plus c. Of course, you can pull out this 1/2 out here. you can pull out 1/2 from this integral. And then if you integrate this one, that is e to the power 2x divided by 2. And with the 2 that you have in front, that will become 1/4. Okay. So this is the answer. All right, that completes the first part. And now let's work on the second part. Let me copy this to the next page. All right, here again, I'm going to apply the integration by parts formula. Perhaps I will copy the formula. All right, here, I'm going to make this identification. I need to identify my u and dv. I'm going to identify here my u to be ln x and my dv to be x squared times dx. Okay. All right. You might be wondering why I make that particular choice. Why don't you identify this to be your u? Because when you differentiate this one, you will get a simple expression, right? But you will see that if you identify this to be your u, you will get a situation where you cannot integrate. You don't have enough information, enough formulas to. You don't have a formula to integrate that particular integral. So I'm making this particular choice here. I'm going to take u to be this function and dv to be the product of these two, x squared dx. So immediately this will give me du over dx is equal to 1 over x. That means du is equal to 1 over x times dx. Here, by anti-differentiating, if you integrate both sides, you get v is equal to x cubed over 3, because the integration of this x squared is x cubed divided by 3. So we have everything we need to go with the integration by parts formula. So let me apply the formula. So my original equation, x squared ln x dx is equal to uv. What is u? What is v? U is ln x, v is this function. uv, that is ln x times x cubed over 3 minus integration. What do we have? v dv. I know my v. v is this one. dv, v du, pardon me, v du. du is this one. I can plug that in here. v du, x cubed over 3 times 1 over x times dx. If you simplify this little bit, you will get ln x times x to the power 3 over 3 minus 1/3 times integration x squared dx. That's what you have. You can pull out the 1/3. Now you know how to integrate this one. As you can see, we brought down this complicated integration to a simpler integration. Now you know how to integrate this one. This should be equal to ln x, x to the power 3 over 3 minus 1/3. You have x to the power 3 divided by 3 plus a constant. This is your final answer. Okay. This is another application of integration by parts formula. Okay. Let's move on. Next, again, I want to apply the integration by parts formula for different examples. Here is the example that I want to do next. Apply integration by parts formula to integrate each of these functions. Let's work on the first part. I'm going to identify my u and dv. Okay. So in this case, I'm going to identify my u to be x squared and dv to be e to the power x times dx. This is my u, this is my dv. Okay. But of course, if you try to identify the other way, if you try to identify this to be u, you will see that you are going to come up with an even complicated integral. Okay. You have to make the right choice. So I'm going to take u to be x squared and dv to be the rest of the thing. So now from this, I immediately get du over dx is equal to 2x. That means du is equal to 2x dx. You send this dx to the other side. Okay, so you get du is equal to 2x dx, and then you anti-differentiate both sides of this equation, or in other words, you integrate both sides of the equation to find your v. That will give you v is equal to e to the power x. Of course, integration e to the power x dx is e to the power x. So we have everything we need to go with the integration by parts formula. Now let's go with the integration by parts formula. Integration x squared e to the power x dx is equal to uv. Of course, integration x squared e to the power dx is same as this expression, that is equal to uv minus integration v du. uv, that is x squared times e to the power x minus integration v du. v is e to the power x, du is 2x times dx. Now, of course, I can pull out the constant 2. You get x squared e to the power x minus 2 integration x dx. Of course, x e to the power x dx. Okay, that's what you get. This is what you get if you pull out the constant. All right, now as you can see, so this integral, this is the original integral, that is equal to this one. Actually, this expression, this integral is better than our original integral. Why is that? In the original integral, we had x squared times e to the power x, but here you have just x to the power 1. That's an improvement, right? This is simpler than the original integral. So still, we don't have a direct way of calculating this integral. So we have to apply the integration by parts formula one more time. Okay. Again, I'm going to identify u and dv, my u and dv. This time, I'm going to identify my u to be this one and dv to be this one. I'll take u is equal to, perhaps I'll write it here, apply integration by parts formula again. Right here, integration by parts. Okay. So here, to apply integration by parts formula again, I'm going to take u is equal to x. That will give me du is equal to dx. Because the derivative of u with respect to x is 1. You multiply dx to the other side, you get du is equal to dx. And I'm going to identify my dv to be e to the power x dx, like in the previous case. You will immediately get v is equal to e to the power x. Now I'm going to apply the integration by parts formula for this integral. Okay, so let me write my original integral as it is. This is my original integral. X to the power 2 e to the power x dx is equal to x squared times e to the power x, that is this term, or pardon me, this term, minus 2 times bracket, I'm going to apply the formula for this one. For this one, again, I'm going to apply the formula, that is uv minus integral v du, integration v du. uv, in this case again, uv is x times e to the power x minus integration v du, that is e to the power x, du is exactly dx in this case. That's what you get. Okay. Now you can do a final simplification here. X squared e to the power x minus 2 times x times e to the power x minus the integration of e to the power x is just e to the power x. Remember, you have to put an integration constant. You can put that constant outside here. Okay, all right. So this is the final answer. So that's how we use integration by parts twice to solve certain integrals. Okay, for this integral, we have to use integration by parts twice. One time is not enough. If you do one time, still you get a product. And if you do one more time, that will get you an integration where you can find the integral. All right, let's move on. Next, we have this theorem, integral of natural logarithmic function. Indefinite integral of ln x dx is equal to x ln x minus x plus c. How do you know that this formula is true? How do you prove that this is a valid formula? All what you need to do is show that this is an antiderivative of this function ln x. Or in other words, you differentiate this function and show that you get this one. If that is the case, this is the integration. This function, this antiderivative plus the constant. Okay, so that's so straightforward. So I'm not going to prove it. All right, next I want to go over this particular example, deciding when to use integration by parts. Okay, we need to determine whether integration by parts or integration by substitution would be better for each integral. Okay, so what about the part one, first part? Okay, for this one, clearly integration by substitution would be better. Okay, integration by parts is not the best strategy in this case, because as you can see, if you take this to be u, the derivative is there. The constant multiple of the derivative is outside. So that's what exactly we want if you want to apply the u substitution, right? So u substitution would be better in this case. If you take u is equal to x squared, that will give you du is equal to 2x times dx. And if you do the u substitution, you will get integration x times sine x squared dx is equal to integration. Notice that you have x times dx here. Here, x times dx is equal to du divided by 2. You have to pull this 2 here. Okay, so we have sine u 1/2 times du. And of course, this is equal to 1/2 times integral sine u du, and you know how to integrate this one. Okay, and you can go from there. All right, let's move on to part B. What about part B? Can you apply the integration by parts here? Okay, first of all, integration by substitution would not be a good option here. If you take this to be u, the derivative is not there. On the other hand, if you take this to be u, again, the derivative is not visible right next to that. So integration by substitution would not be the good strategy. But here we can use, again, integration by parts. Okay, so to go with the integration by parts, I'm going to take u is equal to x squared and dv is equal to the rest of the thing, sine x times dx. I take x squared to be u, and then sine x times dx to be my dv. From this one, you get du over dx is equal to 2x. That means du is equal to 2x times dx. From this one, you get, by anti-differentiating or integrating both sides, v is equal to minus cosine x. Okay, now I can apply the integration by parts formula here. My original integration, x squared sine x dx should be equal to u times v, which is minus cosine x times x squared minus integral v du. V is minus cosine x. What is my du? From this one, pardon me, yeah, from this one, du is equal to 2x times dx. 2x times dx. Now I can simplify this a little bit further. Minus cosine x times x squared plus, I'm going to pull out 2. Here I have x times cosine x dx. Okay, that's what I get if I apply the integration by parts formula. By the way, make sure that you write by integration by parts, okay? You're using this formula. Okay, so if you apply the integration by parts formula once, this is what you get. Nothing to worry about this part. This is just a function. All you need to worry about is this integral, okay? As you can see, this integral, if you look at this integral is better than the original integral or this integral. This is much better because here you had x squared times a trigonometric function. Here you have x times a trigonometric function. So we have an improvement there, right? You have x to the power 1 here. We have reduced the power. So how do you actually solve this integration now? All what you need to do is you apply the integration by parts formula again for this one by taking your u to be this one and dv to be this one. Okay, I'm not going to do that one because we did similar examples before. Apply integration by parts one more time. Apply integration by parts again. You can take u to be x and dv to be cosine x dx. Okay, that should give you the final answer. Okay, that should give you an integral that you can solve. All right, next let's move on to the next part. See, what about this one? Okay, so in this case, what I'm going to do is part C, I'm going to choose to go with integration by parts. I'm going to choose u to be, I'm going to choose u to be ln of x and dv to be x times dx. Okay, I'm going to make that choice. And by the way, try the other way. Choose this to be u and this thing to be dv. You will see that you are going to be in trouble. Okay, you are going to come up with something that you don't know how to do. Okay, so this is the right choice. I'll go with that choice. This will immediately give me du over dx is equal to 1 over x. That means du is equal to 1 over x times dx. Okay, from the other one, I can anti-differentiate this one easily. I will get v is equal to x squared over 2. Now I can go with the integration by parts formula. Integration by parts formula. Let me copy the formula here one more time. All right, by integration by parts formula, we have the integration of our original function x ln x dx is equal to uv, that is x squared over 2 times ln x minus integration v du, x squared over 2 times du is 1 over x dx. Okay, now as you can see, this is an integration that you can perform. You know how to integrate this one, and that will give you the answer. Okay, I'm not going to finish this. Okay, next part D. What can you do about part D in this case? Actually, this integral part D can be solved using integration by parts using both integration by parts and by substitution, but substitution would be easier in this case. Okay, so if you use u is equal to ln of x, that should give you the you should be able to find the integral. Okay, use this substitution and find the integral. I will leave that as an exercise. And then the next thing I want to work on is part E. If you look at that one, before I do anything else, I'm going to rewrite this integral. I have 1 plus x integration of 1 plus x divided by e to the power minus x dx. I'm going to rewrite this as x plus 1 times e to the power minus x dx. I wrote that as x to the power, x to the power minus x. Actually, I made a mistake here. This should be plus x. Okay, you have in the bottom e to the power x, and here it becomes e to the power minus x dx. Now you have a product. Okay, you can apply the integration by parts or integration by substitution, but substitution would not work better in this case. In this case, integration by parts would work better. Okay, so I'm just going to direct you how to identify u and dv, and then I will leave the rest of the thing as an exercise for you to try. Okay, here to apply integration by parts, basically you take u is equal to x plus 1 and dv is equal to e to the power minus x dx. Okay, if you do the other way, if you pick u to be e to the power minus x, you will see that you are going to get an even complicated integration. So you need to go with this choice. Okay, with this choice, apply the integration by parts formula to get the final answer. And then for the last part, clearly, u substitution would be ideal in this case. We solved a similar type of problem in the previous section when we were doing u substitution. If you take u is equal to e to the power x plus 1, that should give you the possible integral if you use this particular substitution. Okay, I will leave that as an exercise because we did that in the previous section. Let's move on. Next, we have this theorem 5.9, integrals of inverse sine and inverse tangent. Okay, the integral of sine inverse x, the definite integral of sine inverse x is equal to x sine inverse x plus square root of 1 minus x squared plus a constant. The indefinite integral of tan inverse x is x tan inverse x minus 1/2 times ln x squared plus 1 plus c. Again, how do you prove that these formulas are true? All what you need to do is show that this part is an antiderivative of this function. Okay, so you differentiate this piece and show that you get sine inverse x. Okay, you will get it if you differentiate. Please prove these two formulas. Very straightforward. All right, moving on. And then how do we apply the integration by parts formula for definite integrals? The procedure is same. Okay, so let's look at this theorem to understand how we can apply integration by parts formula for definite integrals. This is theorem 5.7, formula for integration by parts. If u is equal to u of x and v is equal to v of x are differentiable functions on a comma b, then the definite integral from a to b u dv is equal to, you apply the limit over here, a to b. Basically, you take the integration of this particular function u, that is integration of u dv, and then you apply the x limits. And we know that this is equal to this by integration by parts formula. You apply the integration by parts formula to find this integral to be this one, and then you apply the limits for this piece. Of course, this is just a function. There's no integration. If you apply the limit here, you just get the evaluation notation. UV, you put A to B. And then minus, you put the limit for this integration. A to B. Okay. All right. So let's look at an example for this. Here is the example that I want to look at. How to find this definite integral. Definite integral from 0 to pi x cosine x dx. Remember, we did this example, okay, using integration by parts at the beginning. Right here, okay, we did this example using integration by parts, and we saw that the indefinite integral of x cosine x is this particular expression, x sine x minus sine x dx. Okay, so I'm copying this formula to the slide. Okay, here is the formula. I just copied the result here. The integration of x cosine x is equal to x sine x minus integral of sine x dx. Okay, so now how do you find this definite integral using this formula? Well, all what you need to do is put the limit. You put the limit for this part. I know that this integral is equal to this whole thing. So you put the limit for this part and put the limit for this integral. So this should be equal to x sine x. That's just a function. So you put the limit in the evaluation notation 0 to pi minus integral 0 to pi, the other part, sine x dx. Okay, that's it. Now, of course, we can calculate this one. We know how to calculate this one. You plug in the upper limit and then you plug in the lower limit and find the value. Okay, this will be equal to, if you plug in the upper limit, you get pi times sine pi minus 0. Because if you plug in the lower limit, it will be 0. So we have this first term plus the second term. First, you need to integrate this sine x. The integral of sine x would be, it's not actually plus, you have minus there. Integration of sine x is minus cosine x. You put the limit 0 to pi. And this will be pi sine pi plus, minus minus becomes plus. You have cosine pi minus cosine 0. Of course, you can find these values. You know these values. Okay, so that's the answer. It's all about just putting the limits for your formula. Okay. All right. Here is the last example that I want to go over here. Let's work on this example. Okay, so to apply integration by parts, my plan is to apply integration by parts formula again. So I need to identify my u and dv in this case. Okay, first of all, let me copy the integration by parts formula again. Here is my integration by parts formula. So I need to identify my u and dv. Need to compare this integral against this one. So let me identify my u to be x and dv to be secant squared x dx. Okay. From this one, we immediately find du over dx is 1. Du over dx is 1. That means du is equal to dx. Here, you anti-differentiate. You integrate both sides, then you will get v is equal to tan x. V is equal to tan x, because we know that the integral of secant squared x dx is just tan x. So now we have everything to go with the integration by parts formula. This will give me 0 to pi over 2. My original integral is x times secant squared x dx. That's equal to u times v. that is x times tan x. You have to put the limit. Don't forget to put the limit. Okay. Actually, this is not the right formula. I need to put the formula with limit. So let me copy the correct formula there. Here you have the formula. Okay. So you have to put the limit for UV product. This is the UV product. You put the limit, that is 0 to pi over 2, 0 to pi over, pi over 4. Minus integration 0 to pi over 4 v du. My v is tan x. My du is dx. Okay, that's what I get if I plug that in. Okay, of course, now you can find this piece easily by plugging upper limit and lower limit. Now you need to somehow find a way to integrate this one. Okay, and notice that tan x is sine x divided by cosine x. Let me focus on that integral. You have here x times tan x 0 to pi over 4 minus integration 0 to pi over 4 sine x divided by cosine x dx. Okay, here to do this integral, I'm going to use a substitution. I'm going to use the substitution u is equal to cosine x. Then you get du is equal to minus sine x dx. That means minus du is equal to sine x dx. So if I go with that substitution, you will get x tan x okay, so this is what you get if you do the substitution here. Sine x times dx is equal to minus du. I can put minus du here. And of course, this is your u. You put u there. This is what you get. Okay. Now you can integrate this one, of course, by pulling this minus sign out. That's going to be, by the way, if you plug in these limits, you will see that this is going to be equal to pi over 4. Okay. That whole thing is pi over 4 minus, it becomes plus actually. If you pull out the negative sign, you will get ln absolute value of u. You need to plug in the limits 0 to pi over 4. Okay, if you plug in the limits, you will get pi over 4 plus ln square root of 2 over 2. I'm skipping some details here. Okay, you plug in these limits 0 to pi over 4 in this function. By the way, notice that these are x limits. Okay, so you need to replace this u by x. Okay, you need to replace this u by x before you plug in these limits, because these are x limits. Okay, if you find the limits, you will get your answer to be this one. All right, that completes that particular example. And with that, we conclude section 5.2. I'll stop there. I'll see you next time.